Well, if we're going to be talking about functions and function notation, we should probably know what a function is. Basically, a function described either by an equation or by a graph will make a picture where there can be only one y value for any given x value. What this means is, if I hold a vertical line up to any of these 6 graphs, those that are functions will only cross that vertical line once. So this first one, holding up my vertical line, absolutely a function. The second one, if I hold a vertical line up, gives me a picture that crosses that vertical line more than once. So this one isn't a function. This is just a relation. The third one looks close, and certainly parts of it look like they are a function, but I can find parts of that relation where again I cross the vertical line more than once. This is not a function. Circles, also just relations, not functions. These last two, they're looking good. They are both functions. If I hold a vertical line up, the picture, described by an equation of course as well, only crosses that vertical line once. So again, every single one of these relations, functions or not, can be described by an equation. Both the graph and the equation show the relationship between two variables. We can rewrite it so that the y, the output of the equation, is written in this way. And we pronounce f open brackets x close bracket as f of x. Let me write that down. So this is f of x. What this means is we're varying x and the output is the y. In other words, y is a function of x. This notation, rather than writing y is equal to 3x plus 7, which is a valid way to write f of x equals 3x plus 7, simply another format that highlights to us that the variable we're changing is the x. Or rather, we're interested in the output of the function, what happens to the number on the right-hand side as I substitute in different values for x. We can have x appear once in the function, as we do in this first example, or maybe it appears multiple times, as it does in the second example. This means that when we substitute in different values for x, we have to replace each x with the number that we're interested in. Again, the output of the function, f of x, is the number we get once we've done the replacement. The output of the function is f of x. So in both of these I've used the letter f, but in fact f, while the most common, isn't the only letter we could use. We can just as easily use other letters like g of x or h of x to represent the functions. And that's just so we can talk about multiple functions at the same time and not be worried about calling them by the same names. We also don't have to have x as the variable, but in our case, we're going to stick to that. Which brings us to evaluating these functions at various values of x. So if we're given f of x is equal to 3x plus 7, and we're told to find f of 4, f at 4, that tells us that we're to take each x in the equation and replace it by the number 4. So what's the value of the function when x is equal to 4? That's the question. So f at 4 is equal to 3 times 4, replacing the x with the number 4, plus 7. Or 12, 3 times 4 is 12, plus 7 is equal to 19. So the output of this function when x is equal to 4 is 19. In other words, f at 4 is 19. We can transfer this information into a table. So in this first column, we have a variety of values for x. So for example, if x is equal to -1, we're then asked for the output. So here we'd like to evaluate f given that x has a value of -1. And rather than writing the equation in here, I'm just going to write the answer. So let's evaluate this separately. F at -1 tells us, well, I'm going to take the x's in the original equation and replace them with a -1. So we have 3 times -1 plus 7. In other words, -3 plus 7, or 4. So if x has a value of -1, f at -1 is equal to 4. In other words, we've found an xy coordinate. The xy coordinate that we found is -1, 4. We can use this information to draw a picture, to draw a graph of our function. Try the remainder here. What happens if I substitute in 0 for x? Well, we get 3 times 0 plus 7, or just 7. Try the next two. F at 1 has a value of 10, and if I substitute in 7, I find that f at 7 has a value of 28. So now we have 4 coordinates, which for a straight line, this function is a straight line, is 2 more than we need. And in fact, we'd already found one. We'd found the coordinate 4, 19. So we can plot these points on a graph, on a coordinate plane, connect the dots, and we have a picture of our function. So I've reproduced our table here using the same function, f of x is equal to 3x plus 7, the same table. We have these 4 coordinate points that we'll plot on the graph. So let's first graph the point -1, 4. So that's negative on the x-axis, -1 on the x-axis, and positive 4 on the y-axis. There's the point, -1, 4. The point 0, 7 is 0 on the x-axis and 7 on the y-axis. So we're up here. For this particular function, f of x is equal to 3x plus 7, 2 points is enough. And that's because this is a linear function. How do I know it's a linear function? The highest power that x is raised to is a 1. So in this case, the 2 points were enough. I didn't have to graph 110 and 728 in order to get an idea of the relationship between x and y. This one's a little bit more complicated. In fact, what shape is this function going to be? Because the highest power that x is raised to is a 3, this is a cubic function. It's good to know what shape our graph is going to have before we start plotting points and connecting them so that we know how we should be connecting them. If you're not sure how to tell which function we have, go back to the general shape of functions video. In any case, for this particular question, all we're being asked to do is evaluate f of x for various values of x. Let's try a few of these. To evaluate f at -3, we drop -3 in for every instance of x. What you'll notice is that I put -3 in brackets, and that's going to become extremely important. Remember that there's a difference between -3 in brackets all squared, which means -3 times -3 and gives positive 9, and -3 not in brackets squared, which gives us -3 times 3, and therefore -9. Because all of x is squared and all of x is cubed, and our x has a value of -3, we have to be careful to put our value in brackets. Now for cubics, it doesn't matter. -3 cubed and with or without brackets gives us -27. But then we have -2 times -3 squared, so -2 times positive 9, and finally plus 4. There's a constant at the end. So we have -27 minus 18 plus 4, which gives a value of -41. Let's try a positive number. Let's find f at 1. Well, now I'll take 1 and cube it, subtract 2 times 1 squared, and finally add 4. That gives me 1 minus 2 times 1, or just minus 2, plus 4. And here we have positive 3. Try the remainder of the values of x to fill in this table. One thing I notice right away is that the numbers oscillate oddly. We go from negative 41 up to negative 12, up to 1, up to 4, and then suddenly we're down to 3 again, but then back up to 4, and then very rapidly up to 13, even though we've only varied x by 1. And this is common for cubic functions. Let's have a quick look at what this function looks like. We do find that although if x is equal to negative 3, and even when it's equal to negative 2, that it goes below y is equal to negative 3, we do find our points negative 1 and 1 right there, 0 and 4, 1 and 3, 2 and 4, and then when we hit to 3, we're headed up towards 13. So those values have given us a good idea of the key part of this function. The key part of the cubic function is where we have this whoop-de-doo in the middle, and that it increases as we continue increasing x. This function continues to increase up and to the right, and it continues to decrease down and to the left. These two weren't points on the graph. I was just highlighting the values of x. The only points from our table of values that fit onto the graph as I've captured it here are the 4 you see. And then finally, what if x is not a number? What if it also contains variables? Using function notation, this is very easy to do. So for this first question here, we're familiar with the first one. If we'd like to find the value when x is equal to 0, we simply substitute 0 into our function. So we find we have 5 times 0 minus 2 divided by 3 times 0 plus 7. 5 times 0 is 0, 0 minus 2 is negative 2, and in the denominator 3 times 0 is 0 plus 7 is equal to positive 7. We might want to write this as negative 2 over 7, rather than keeping the negative in the numerator. So that's f at 0. But what about f at 3x? Well, you're going to do exactly the same thing. Everywhere that we see an x in the original function, we're going to replace it by 3x. So we get 5 times 3x minus 2 divided by 3, also times 3x, that's where we see an x in the original function, plus 7. We can simplify this somewhat by doing the multiplication of 5 times 3x. It's fairly straightforward to do, so we have 15x minus 2 divided by 9x plus 7. Depending on the question, we may or may not be asked to expand. For example, for the second question, I'm not going to ask you to expand the outcome. This one's got even more going on in what we're being asked to substitute in the original equation. And this is an example where we've used the letter g to name the function. So we're told that g of x is equal to 3x squared minus 5x plus 1. And everywhere that we see an x, we're going to replace that with 2x minus 1. So we get 3 times 2x minus 1, all squared, minus 5 times 2x minus 1 plus 1. I'm going to leave this one as is and not expand it.